Hello there. So, in this lecture, we are going to be answering the question that I'm sure was on everyone's mind. How do we find the eigenvalues of a matrix, right? So, remember and so this is video number 1 of section 5.2. So remember section 5.1, we introduced this sort of concept or value/vector called the eigenvalues and eigenvectors of a matrix. And what we did with them was, we sort of verified, okay, here's how we can check if something is an eigenvector. Fairly straightforward process. Here's how we can check if something is an eigenvalue. Less straightforward, but doable process. What we didn't do was talk about, what if I'm given a matrix and I have neither, and I want to actually just find the eigenvalues of this matrix? We have a way. So, for any n by n matrix, and so this isn't just for this example. I'm going to certainly work through this example. Remember, we know that the eigenvalues must have the property that this matrix is non-invertible. Lambda, where x here isn't equal to the 0 vector, right? So again, if lambda is an eigenvalue, then this homogeneous equation has a non-trivial solution. Well, we've learned a lot about, thanks to the invertible matrix theorem and some other occasional theorems which we've proved, we have learned quite a bit about matrices, specifically when those matrices have non-trivial solutions to this equation. One thing we've learned quite recently is that the determinant of this matrix is zero, right? So if a non-trivial solution exists, so that is if lambda is an eigenvalue, then the determinant of this matrix is equal to 0. Well, we have a way of calculating determinants using cofactor expansion, right? So what we can actually do is basically take this matrix, treat lambda as a variable, and solve for the values of lambda which make this equation equal to 0. This might look familiar because I think this was the extra credit question on your midterm. So I'll show you how we do just that. So here's the example. So we want the determinant of the matrix A minus the diagonal matrix with lambdas on its diagonal. Right, so notice that this matrix is now, going back to this example, the matrix we want to calculate the determinant of. Well, so we can write this a little more compactly using our determinant notation and by combining these two matrices. And so this is equal to 5 minus lambda times -3 minus lambda plus 12. And so working this through, if you distribute and sort of factor everything, you get the polynomial lambda squared minus 2 lambda minus 3. I'm glad I'd worked that out beforehand because my mind was just not wanting me to do any algebra at the moment. And so, well, what do we want? We want then all of the values of lambda which make this, which is this determinant, equal to 0. So we want to set this equal to 0. And I'm going to put that in a red box because we will talk about this, well, I guess this whole sort of process in a second. But notice that I can factor this. To lambda plus 3 times lambda plus 1. And so the eigenvalues of A, there are 2 of them. Lambda 1 equals 3, and lambda 2 equals negative 1. And so notice, this actually shows these are the only 2 possible eigenvalues of A because of the way we've worked this through. We've just let lambda be this sort of mythical, mysterious variable at the start. And sort of worked our way through and showed, well, the only 2 values of lambda that can make this equation 0 are 3 and negative 1. So these are actually all of the eigenvalues of A. And then certainly we could find the eigenvectors, and we'll look at an example of this later on, I think in video 3 of this section, how to then actually find the eigenvectors, which we kind of saw, but we'll go through the whole process once or twice, certainly at the end. So this red boxed equation here is called the characteristic polynomial, or characteristic equation of A. And so I'll define this formally now. But basically the way we find eigenvalues of a matrix is by calculating its characteristic equation. Because the roots of this equation are always the eigenvalues of the matrix. So the equation, and so in general, this is the determinant of A minus lambda times I equals 0, is called the characteristic equation of A. And so here I'm sort of implicitly assuming in this definition, characteristic equation. So I'm implicitly assuming in this definition that A is a square matrix and that I matches the dimensions of A. Its roots, and so that is the values of lambda which make this, which satisfy this equation, are the eigenvalues of A. And so notice every eigenvalue is a root of this equation, and every root of this equation is an eigenvalue. So that's actually basically the main topic of this video. I just want to go over 3 examples and then define one more thing that will sort of pop out of these 3 examples. So let's first look at a 2x2. And so actually, for all 3 of these, I highly recommend, again, like with most videos, pausing the video here and trying to work through all of these on your own. 2 and 3 are increasing in dimension, and while we haven't yet seen an example of those, it actually sort of, as we increase in dimension, it generalizes in the same way, that you want to just calculate this polynomial. And as you'll see, with 3x3 matrices, you're going to have to do cofactor expansion because of those lambdas. And so getting beyond 3x3, it kind of starts to get unrealistic to do it by hand. Maybe a 4x4 with some easy cofactor expansion. But anyways, we'll talk about that as we move on. So in all of these examples, I guess I'll put directions here. Find the eigenvalues / characteristic polynomials. Polynomials of the following matrices. And we'll do them one at a time here. But keep these matrices handy, so I'm going to do them one at a time on the board. Keep the solutions handy because I will come back to each of the solutions we get after I define sort of our last definition of the video. So, first example, and again, all of these are on the worksheet as well. 7, 2, negative 2, 3. And so remember, the characteristic polynomial is found by taking the determinant, where I subtract lambda from each of the diagonal entries of A and take the determinant. So it's the determinant of this matrix. Expanding that, I get 7 minus lambda times 3 minus lambda plus 4. This is equal to lambda squared minus 10 lambda plus 21 plus 4, which is equal to lambda squared minus 10 lambda plus 25. And so the characteristic polynomial or equation, so a sort of brief but I guess necessary distinction, and you'll never really be expected to, well, there isn't really much of a difference. It's just sort of a name. This is the characteristic polynomial. And this is the characteristic equation. So the only difference is in one we're setting the characteristic polynomial equal to 0. There's really no difference between them. Your book does define them differently, but just sort of keep that in mind. The characteristic polynomial is just the polynomial part of the characteristic equation where all you're doing is setting this polynomial equal to 0. I'll probably just use them interchangeably. I would know this for the homework, right? The homework might talk about them differently, but certainly like on quizzes or tests, I won't, I'll consider these the same thing. So, if you get asked to find the characteristic polynomial or equation, either one of these will be fine. So anyways, to find the eigenvalues, we want to find the roots of this, and I think factoring this, we get that. So notice here, there's actually only one root, which is lambda 1 equals 5. And so, technically this is lambda minus 5 times lambda minus 5, right? And so they're, I guess, two factors, right? But they give the same root of 5. We would say that 5 appears as a root twice in this equation, or that 5 is a root with multiplicity 2. So keep that in mind, because the last definition we introduce after doing our next two examples will sort of use this sort of idea of an equation having multiple factors corresponding to the same root. All right, so let's move up in dimension. Next up, we want to do a 3x3 matrix. So we want to find the characteristic polynomial and the eigenvalues of the matrix 5, negative 2, 3, 0, 1, 0, 6, 7, negative 2. So doing this, we want to first calculate the determinant of the matrix, where I subtract lambda from each of the diagonal entries. So as you can see, as we approach like 3x3 and 4x4 territory, you could definitely envision a moment where this could kind of start to get annoying, and I agree. So we want to try to use our full bag of tricks that we have for determinants here. But notice, one thing. you might be tempted to row reduce. And certainly that's a way you could do it. Sort of the issue with that is that you're going to, you sort of have the potential to wind up with a lot of lambda terms, like, right? So, if I was going to row reduce this in order to find its determinant, right? And eventually you'll probably have a 3 by 3 matrix where, so notice here the cofactor expansion on this one, as we'll see in a second, is going to be relatively straightforward. But at some point in the course, you'll probably have a 3 by 3 matrix that you have to just pick sort of a row with all constants, cofactor expand, do a lot of algebra in order to find the eigenvalues. Beyond that, if you're given a 4 by 4 or a 5 by 5, I pretty much can guarantee there's going to be some trick, as we'll see. But so, or, it'll be really easy to start with the 4 by 4 and, contract it down to a 3 by 3 or a 2 by 2, then that will make it easier. So, like, if you're going to do a full cofactor expansion without having a nice 0 row like this, it'll generally involve at most a 2 by 2 or a 3 by 3. Anyways, doing these row operations, right, the first row operation would be to get rid of this 6. But as you can already see, this would introduce tons of new lambdas into the matrix, which I don't really want. And so barring like having an upper triangular matrix, generally the best way to just go about calculating the characteristic polynomial once we introduce these lambdas is to use cofactor expansion. So we're just going to expand across the second row. This is equal to now, let's see, so that's row 2, column 2, so that should be 1 minus lambda. And so remember, this would be times negative 1 to the 4th, since it is in row 2, column 2. So we don't have to change the sign of this. Times the determinant of, well, I want to eliminate rows 2, columns 2, so this should be the determinant of 5 minus lambda, 3, 6, negative 2 minus lambda. Well, now this is just a 2 by 2, so we can expand this. So this would be 1 minus lambda times 5 minus lambda times negative 2 minus lambda minus 18. And I will let you, well, I can do 1 or 2 more steps here. So the way I would then, I'd actually never factor this, so you should get lambda squared minus 3 lambda minus 28. And so what I would never do is try to then factor this 1 minus lambda through, because notice this is already a root of the characteristic equation, right? Sort of just if I plugged in 1 for lambda, then it would make the whole thing 0. So you actually, if you have a nice factor like this that's already a linear factor, just leave it alone. There will be some times where you do want to factor it through and refactor everything again, as you'll see. But if you can easily factor the inside, which I guess as factoring goes, this one isn't horrible. This should factor to lambda minus 7 times lambda plus 4. Notice at this point we've already split this polynomial into its 3 linear or single degree term roots. And so calculating the characteristic polynomial, we can see that the 3 roots of this equation are lambda 1 equals 1, lambda 2 equals 7, and lambda 3 equals negative 4. And so those would be the eigenvalues then of this matrix B. So again, there's a little bit sort of, being able to, there's a little bit of practice, I think, that'll go into, sort of eyeing these polynomials and determining when to factor and how much to factor. But I could kind of tell here, like, since this factor was linear and I kind of expanded the inside and noticed that this would factor nicely right off the bat, I just left that 1 minus lambda alone. All right, so one more. And so notice in particular, too, then, each of these roots appears exactly once in the characteristic equation, polynomial, whichever one you want to call it. All right, one more example. And here I will reveal some tricks. Well, yeah, it's a little bit of a trick. Although, if you were to calculate this using cofactor expansion, you could do it relatively quickly. So we want the characteristic polynomial and the eigenvalues of this matrix. Well, we already know what the eigenvalues are, right? Because this is an upper triangular matrix. And actually, just for the fun of it, so we've already proved in one way, right, by sort of selecting the correct values of lambda here, that the eigenvalues have to fall on the diagonal. But now we can prove using characteristic polynomials, actually, that. So I'm going to do this in a slightly longer way than is necessary, just to show that by defining eigenvalues using the characteristic polynomial in this way, we still get this nice result with upper triangular matrices. All right, so I calculate the determinant of this matrix. And so for the moment, let's pretend that I didn't know what the eigenvalues of this matrix were. I might pick either the first row or the first column to cofactor expand. And so I'd get the following expanded determinant. Or again, notice here, because all of the other entries are 0, I'm left with only this term. But then I can just pick, maybe this time I'll pick the first row. Well, then this just turns into the following. And so you might see where this is going. Calculating this determinant, sure enough, sort of what I expected to happen. We get the following characteristic polynomial. And so, of course, we could have actually sort of guessed that right off the bat. Numerous points, right, that certainly we know that the determinant of an upper triangular matrix is just the product of its diagonal entries, so I guess I didn't even need these steps. We've already proven this fact. But also on top of that, we know that the eigenvalues of an upper triangular matrix are on its diagonal. I guess the one thing we didn't yet sort of show, notice that here with this upper triangular matrix, 3 appears on the diagonal twice, and 3 minus lambda appears twice as a root in this characteristic equation. And so again, this is sort of like number 1, that when counting eigenvalues, we don't count 3 twice. So we would say that this matrix has 3 eigenvalues, 4, 1, and 3. And that would be that. So I kept mentioning these matrices that have these eigenvalues that appear multiple times in our characteristic polynomial. So we actually have a name for that and a way of describing that and a way of talking about that. So I want to wrap up with one more definition, and then we will relate that definition to the 3 examples we just looked at. All right. So the number of times that an eigenvalue appears as a root in the characteristic polynomial is called the algebraic multiplicity. And so the reason we put algebraic before it is that there is something called the geometric multiplicity, which we will talk about potentially later on. An eigenvalue. of a matrix A is the number of times it appears as a root in the characteristic. I hope I spelled that word right. I realize now that I'm not 100% confident in my spelling of the word characteristic. If I'm spelling it wrong, let me know. Certainly don't want to embarrass myself too much. So the algebraic multiplicity of an eigenvalue of a matrix A is just the number of times it appears as a root. And so as an example, we'll go back through the matrices A, B, and C we looked at in our previous 3 examples. So remember, A had one eigenvalue, lambda 1 was equal to 5. Well, this has multiplicity 2. And until we introduce geometric multiplicity, like I said, there's 2 different types. If I refer to multiplicity, I'm referring to this specific definition. So for now, if you hear multiplicity, I'm asking for number of times it appears as a root in the characteristic polynomial. Second matrix we looked at, B. Lambda 1 equals, I have to remember the 1, 7, negative 4. Lambda 2 equals 7. Lambda 3 equals negative 4. All of these eigenvalues have multiplicity 1. Right, because if you remember the characteristic polynomial of B, each appeared as a root exactly once. And finally, matrix C. Again, we had 3 eigenvalues. Lambda 1 and lambda 2 were the eigenvalues 4 and 1. And so each of these eigenvalues have multiplicity 1. And the last eigenvalue, lambda 3 equals 3, had multiplicity equal to 2. So the algebraic multiplicity, or like I said for now, just the multiplicity of an eigenvalue, is just the number of times that eigenvalue appears as a root in the characteristic polynomial. So we can now find eigenvalues. Video 2 will introduce a fun yet, fun concept.